Thank you, Natalia, for the nice introduction. And thanks to the organizers for inviting me and giving me the opportunity to speak about some recent work that I have, which will involve, I guess, some of the topics that we had. Good point. Yeah. Which will talk about some themes that we've been hearing about this week and last week in this workshop. So, this is not. Let me see, maybe I just have to click. Yeah, okay. I'm going to just give you a quick sketch outline of the talk. I'm going to give some physical motivation for why I'm talking about the things that I'm talking about. I'll give a kind of basic introduction into RTA kinetic theory, maybe a little too basic, but I think it's nice to actually establish what I'm talking about in that sense, catching it in the correct terms. Then I'll provide some of the results. This is this first work with, I didn't actually say this, with Matej Bayets, who's a PhD student now in the University of Ljubljana, and Sasha Grozdanov, who's here as well at the workshop. So, so then I'll talk about some of the results, which will be predominantly describing the analytic correlators and the extraction of certain important transport coefficients. And then towards the end of the talk, I'll give us an outlook how we can go beyond the standard story in the RTA and go into maybe higher levels of the BBGKY hierarchy. So, very simple statement at the beginning. Thermal correlators are important, especially of conserved operators, because they carry important transport information. And to kind of underline this, I like this picture from Kurkela, Wiedemann, and Wu that I've kind of reshuffled a little bit. But kind of the idea is that we're trying to describe some sort of physical system. Here, the context of this paper, they were talking about the quark-gluon plasma. And there's some, if you look at linear response theory, there's some analytic structure here, which is ultimately unknown. And what we do as theorists, we try to come up with different descriptions that describe relevant aspects of the physical system and hope to glean some information from this. So there's like the strong coupling approach. This is the analytic structure that's very typical in coming from ADS-CFT, gauge gravity duality, where you have this so-called Christmas tree. They kind of like to highlight in this plot that all these theories have this hydrodynamic pole. This is the diffusion coefficient. It's a little small to see maybe. There's also descriptions that we've heard a lot about, actually in these last 2 weeks, about Israel-Stewart hydrodynamics. So there's some hydropole with some non-hydrodynamic degree of freedom. And I'll be focusing on, we've heard a few talks from Jean-Paul, for instance, yesterday about RTA kinetic theory. And the typical analytic structure is, again, you have this hydrodynamic pole, and you have this branch cut at a depth of the relaxation time. And kind of to further motivate this talk, these correlators in strongly coupled theories have been computed extensively. This is a non-exhaustive list by any means, just some papers I found for different geometries with charge, with rotation, and also even some finite coupling results. And kind of to compare to kinetic theory, to weak coupling methods, there's a bit of like a paucity of results. So the first paper that I could find really that was doing something about the analytic structure of kinetic theory was due to Paul Romachka in 2015. There's been some follow-up works of Kurkela and Wiedemann, including also this one, I guess, involving Bin Wu. And I hope to add more here during the course of the talk. This is kind of the theoretical motivation. Yeah, sorry. Yes. Yeah. I don't know what you mean, but I'm happy to discuss this with you further. Uh-huh. Hmm. You mean these effective field theories of like diffusion of Lucadelic? No, no. Okay. Uh-huh. Hmm. I'm not. I won't talk about this now, but I'm happy to discuss this with you afterwards. Yeah. So yeah, I have all my non-hydro modes. I like to think are gapped in this for yeah, yeah. Okay. Good. So kind of that was a kind of a theory motivation, and now from a more well, what kind of questions am I trying to answer in this talk? So the idea would be to understand the analytic structure of these correlators coming from the Boltzmann equation in the presence of an external electric field and in the vicinity of a temperature gradient. So in 3+1 dimensions, this has applications to the quark-gluon plasma. So there's this picture from that Xun Chen also showed during this workshop. This will also have applications in principle to cosmology. I'm also will show results in 2+1 dimensions. This has clear applications in condensed matter. And also, because it's easy to do, we can also include the presence of impurities, which are not standardly described in your kinetic theory. And I'll talk about how we include this. Like the title says, the method will be RTA kinetic theory. And the results, to kind of get ahead of myself, will be these analytic expression of correlators, and in particular, these thermoelectric transport coefficients. Okay, so here's some recap of kinetic theory. The key object is the one particle distribution function, whose evolution is given by a free streaming piece. So this is just in the presence of some external forces. And on the right-hand side, there's some collisions. The collisions are essentially telling you how the system is dissipating. It can capture inelastic scatterings and things like this. And in practice, it's very complicated. So you can have like 1 to 2 scattering, 2 to 2 scattering, all possible scatterings. You can have many species. I'll focus on one species of particles right now. Okay, so then the idea from this BGK approach and the Anderson-Whitting relativistic version is to replace this complicated collision kernel with this RTA equilibrium function. And so this will be, I'll be talking about the Boltzmann equation, the linearized Boltzmann equation in the presence of an electric field, also in the presence of a gravitational field. There'll be a relaxation time, which will be a constant. I won't put in any momentum scales or anything like that. And I'll have Maxwell-Boltzmann distribution for the equilibrium that the system will relax to. And yeah, just to also make things further simpler and more analytic, I'll be working with a massless gas at with p² set to 0. Good. Okay. Then, okay, very straightforward thing. These, maybe I can go even fast on this, but if you integrate over your moments of the distribution function, you get some macroscopic quantities such as the number density. Integrating with a weight of p mu, this will give you the current, the number current, for instance. And over p mu, p nu, this will be the energy momentum tensor. Good. One more ingredient, we better have that our system actually satisfies some conservation equations. So we start with I've just will write this in the absence of external fields, but the story generalizes the same way when you include external fields. But if we integrate the Boltzmann equation over momenta, you see, remembering that the current, for instance, is given like this. You can just pull this derivative out. This will just be nothing but the divergence of your current. And that's the left-hand side. And the right-hand side is this, this piece here. And so if you want the current to be conserved, you need to require that this term vanishes separately. And this is kind of the statement that you have the conservation of your currents and your energy momentum tensor lead to these RTA matching conditions. So this is a consequence of the conservation equation. So this is over the first moment, and this is over, well, for the conservation of the energy momentum tensor. So far, so good. Okay. Good. Now, I'll kind of just quickly outline the linear. Yeah, sure thing. Ah, I'll get it this time. Okay. Yeah, I wrote this a bit. Yeah, there shouldn't be this. Yeah, there should be P0, and yes, there's a typo. Yeah. Yeah. Yeah, that's right. Yep. Mhm. Sorry? One type of particle, yeah. Yes, and yeah, that's right. Yeah. Yes, massless, yeah. This is just because it's simple. You get closed form expressions that are manageable. But you can do this with massive gas without a problem. It just becomes numerical exercise in that sense. I can comment on this as well. This U, um, well, you want this to be the energy essentially, right? So this is, U is the for velocity, huh? Right, but F equilibrium contains information about the macroscopic quantities. So the kind of, yes, you're right that the left-hand side is, that's right, yeah. I don't know if I have a deeper comment than that. This is the form of, yeah, this is like, I'm taking this to be the RTA right-hand side, yeah. Yeah, okay. Rajiv, did you want to comment anything or? No? That's right. That's right, yeah, yeah, okay. Good. Right, so now I'm gonna do some linear response. For my sources for the electric field, there's basically the gauge field, and to induce temperature gradients, there'll be a metric perturbation. These sources will change since I'm adding electric and temperature gradients. This will change the equilibrium values that are found in the equilibrium distribution function on the right-hand side of the Boltzmann equation. So the temperature will change, the chemical potential, and the for velocity. And this is pretty standard. And this will induce, as a result, just to show how everything really works, the equilibrium distribution function will be changed by a little bit, these quantities here, first order in these changes. And also the one particle distribution function, the true value will be changed. So I'll be trying to compute this. Okay. They are the same. This is notational just to keep it separate. But yeah, you want the F naught is the, it's okay. F naught is the leading order solution to the Boltzmann equation. And it happens to be that if you want this term to vanish, F naught is equal to F equilibrium. This is just bookkeeping to be precise. So F naught, sorry. F naught P will be really the Maxwell-Boltzmann distribution with these parameters. Yeah. Sorry? It's unperturbed, yeah, that's right. So I'm expanding around, yeah, that's right. The leading solution to the Boltzmann equation. Yeah. Okay. So in that case, I can just write down what the linearized Boltzmann equation, how it reads. So I've already used the leading order equation. So everything now is perturbed. So delta F is the same order as the electric field. The Christoffel symbol contains delta G, the metric variation. And then there's delta F again and delta F equilibrium. And because this is in Fourier space, this is really easy to solve. And you have delta F given in terms of these external sources, and also delta F equilibrium, which contains information about how your equilibrium distribution function changes. So then you integrate this, you get the current, the energy momentum tensor, and the thing that's kind of left over, which this is maybe the trickiest part, is that delta F equilibrium contains information about how the temperature changes, how the chemical potential changes, and how the forward velocity changes. These are hydrodynamic quantities or macroscopic quantities that are on the right-hand side. But now, when I do this integration over momenta to get the current and the energy momentum tensor, essentially there's a relationship between the delta J0, for instance, and the chemical potential. This is the change in the number density is given by the susceptibility times the chemical potential. So you have on both sides of the equation, you have to solve for delta T, delta mu, and delta U mu when you are looking at the moments directly. And so this leads to some algebraic manipulation that you have to do to solve for these variables. And then you're left with an expression which is just entirely given in terms of the external fields. And everything is a function of omega and k. Yeah. Yes. Yes. That's right. Mm, that's right. Yeah. Yeah. I mean, if you want, I can just write this. So delta J0 is delta N, and this is the susceptibility delta mu, and that would be like the left-hand side. And then delta F equilibrium contains delta mu. And then, yeah. You have to be, yeah. So this is I wrote, yeah, you're right. Yeah, sorry. I wrote this quick. This is for constant temperature. And then, yes, you have the whole susceptibility matrix in principle, and then you have to be careful. Yeah, good. Okay. And yeah, and then what I'm going to employ is this variational approach. So I can just expand my current in terms of the leading piece, which I'm not super interested in. Then there will be the linear response due to this external gauge field. This is the JJ correlator. There will also be this mixed correlator coming from these temperature gradients. Likewise, the energy momentum tensor will have the stress tensor correlator due to this external metric. And it'll also have this mixed correlator here. And so I'll be now presenting results for these computations here. So that's the theoretical background. Now it's, oh no, there's one more thing, sorry. One more ingredient that I'll include is, because again, this is easy to compute and that maybe has some nice physical meaning. So for now, I was just considering these gas of blue particles just flying around. They're relaxing to equilibrium. But in real systems, you might have some really slow-moving impurities and very dilute impurities that are present, which will modify your conservation equations. This is just really straightforward to add. So here we have the usual RTA term. Here we add another term which is proportional to gamma, which is telling you how much you're breaking momentum conservation by. And this leads to, the momentum conservation, momentum relaxation in the conservation equation. So you see that there's the non-conservation of one of the three of the components of your energy momentum conservation. And in principle, this has been studied also by this group in Genoa, and for the case for you have also relaxation in energy, you have some relaxation in the number density, things like this. This has been studied, and we do this because also holographic theories have made similar computations with this breaking. We can do this without much problem. You just add this one extra term here. Okay, so yeah, the momentum relaxation will be given by this gamma parameter. Okay, good. So results. Yeah. So yeah. So the for this will be like minus I omega plus gamma T0I or dt. Yeah. This leads to this relaxation. And yeah, and this is kind of the picture you can have in mind. Like you have some impurity, there's very few of them, and you're not, in principle, you should also incorporate, again, a Boltzmann description, but here it's just saying, well, they're not really doing all that much. But what they're doing is, for the system that you're tracking, it's making your momentum slow down a little bit, and precisely by this quantity gamma. Okay, so there's this helpful table, but there's this conversaciones. I don't know if this is in the way. Yeah, I'll put this up here. Okay. Yeah, so I'll be spending the next few minutes talking about this kind of way we decided to summarize our results. So it's kind of like a periodic table. I mean, don't take that too close to heart. But essentially here you have the JJ correlator. So this is the current correlator decomposed into spin 0 and spin 1. Then there's the energy momentum, the stress-stress correlator, and then there's the mixed channel here. And then going down, we have finite temperature results. These are the first 3 entries. In the absence of momentum relaxation, in the case that momentum relaxation is along the direction of the perturbation, and momentum relaxation, which is transverse to the perturbation. And here there will be the same thing, but now at finite temperature and finite chemical potential, finite density. So that was describing the left and right side. And now I can describe, like, for instance, we can look at this guy here. So the black points will denote poles, which I'll talk about at length in the next few slides. These squiggles are logarithmic branch cuts, which are typical to RTA kinetic theory. They have a branch point, which is given here, plus minus k minus I over tau r. And actually, just to answer your question from before, I mean, if you have a mass, this will modify this coefficient here. So it'll be, so this is, everything is traveling at the speed of light in this, yeah. Okay. These red arrows, which I'll also talk about, will denote these quasi-hydra modes where you have some diffusive modes colliding and leading to a finite real part. They become propagating modes. And yeah, these channels are just coming from the fact that you have a vector pointing in one direction, you have these SO2 symmetry around, and this is just a handy way to decompose this. Okay, so this first row was computed by Ramachke in 2015. For the massless case, there's also some results from 3 days ago on Easter for the massive case. But yes, I'll just walk through point by point. So Paul Ramachke computed, for instance, this guy here. This is exact. You see, you have this logarithm, and you have this denominator. This is coming from the fact that you have this matching condition. And yeah, you can solve for omega, expand for small k, and you see you have a diffusion pole, and it goes like, I mean, the diffusion is, there's only one scale in the game, it's the relaxation time divided by the space-time, by the spatial dimension, which is 3 in this case. Yes, and so now I'll tell you about what a physical interpretation of the branch cut, which you see there was this logarithm that was in the correlator. So kind of to set the scene, let's picture a massless gas without any interactions. Then I send in a plane wave. I perturb it in, say, the z direction. This leads to, yes, okay, this picture again from Quirkel and Wiedemann. This leads to overdense regions, which are, this is like the peak of the wave, are these black lines. And they kind of propagate through this massless, non-interacting gas. And then an observer is sitting, for instance, I'm sitting here at this x, and the causal reach of perturbations that can reach me if I wait long enough, this retarded time, this c times time, there's different ways the signal can approach to me. So if it's coming from on the same, so let's say I'm at the top of the wave. If it's coming from the same top of the wave to me, then I don't really notice any difference. So here there's essentially zero signal that I'm receiving. Whereas if it's coming from 90 degrees separate, there's maximal difference, and I really feel this signal. So if I want to, yes, and these different signals that arrive, they essentially correspond to different poles. And so you see there's, okay, I'm just doing this in a discrete way. There's, from every angle, from every direction, they come here. So the green one is basically zero signal, and then the red one is the maximum one here. And this is also kind of a causality thing. I mean, this is why the branch point is that omega is plus minus k. And now, but the response, like, I don't care. I need to just integrate over all directions. So I see that this assembles itself into a logarithm, which basically is this collection of poles becomes, once you integrate over, you basically get this branch cut. So that's the really simple argument. And yeah, in the RTA, you also have this relaxation time. So there's some interactions, and this moves the branch cut deeper into the complex plane. If you have a mass, then this velocity, you also have to integrate over momenta. And so this changes the structure of your logarithm. And it's a logarithm also in 3 dimensions, as we'll see in 2+1. The structure changes a little bit. But yeah, the basic principle is seen in like HTL computations. You see this in recoupling QFTs. And this is a particularly simple setting for this. Okay. Ooh, so then moving on, so now this logarithmic structure, because these expressions, although exact and analytical, get a little unwieldy. So I'll introduce this shorthand L here. And looking at, for instance, the energy-energy correlator, you see you have 2 poles. These correspond to the sound modes. So again, this was computed by Palm. This is 1 over square root of 3. It's 1 over the spatial dimension, the square root of 1 over the spatial dimension. And again, you have this branch cut structure, which is just coming from this logarithm here. And finally, you have the shear channel. This has no poles, so hence there's no black dot. But what you obviously can extract from there is some pertinent information, a nice transport coefficient, which is the shear viscosity over the entropy density, which is just given in this dimensionless combination divided by 5. The spin wave, yeah. Okay, that's all well and good. So kind of, yeah. If I were to remove it, yes, yeah. Yeah, I think so, yes. No, yeah. Yeah, I think, yeah. Yeah, I think so, yes. Okay, good. So now if we have just kind of focusing on features, you see that there's some inherited structure when you have, when you introduce momentum relaxation in the parallel direction. So I won't talk about these ones because they basically look the same. So the first novel one is the energy-energy crossover. This is what goes by the name of quasi-hydro crossover. There's I mean, I just picked a nice plot I like from this paper here, but this is the essential picture. You have this combination. This is going in the the parameter is going inverted how we do. This is as a function of momentum. I think this is the other direction, but okay. But what we're able to see is that this collision happens at a precise value of the momentum relaxation scale. Again, I think this is this the factor of spatial dimension. And so this is what this collision looks like if we zoom in on this plot. So this is as a function of k, of momentum. There's some collision that occurs, and then the poles move away, acquiring a real part. And yeah, we're able to compute this exactly. Here's the full structure in all its gory detail, but as you see, it fits on one slide. It's not that terrible. Good. The next thing that's kind of interesting that occurs is if you go to finite density. This is finite density and temperature. What we find in RTA kinetic theory is that there's a factorization that occurs in the analytic structure. So you have both sound and diffusion. And what the factorization means is you literally have a term which looks like it's coming from the density-density correlator. And there's another term which has these sound poles, but there's no interaction between them. Basically, if you run this as a function of momentum, this pole just goes straight down. The diffusive pole runs like k squared, and the sound modes just have some very little motion like this. And yeah, this, just in case you're wondering, this branch cut is just drawn at some finite k, just for orientation's sake. Yep. Yes. Yeah. Yeah. Okay. So much about 3+1. In 2+1, the story again is very similar, except now. Okay, so I can just maybe, yeah. So you have these black points. These squiggles now are these square root branch cuts, but they're also the branch points are in the same place as before because we're at in the massless case. And what we see now is that there's two types of collisions. One, which is what I discussed before. These are these quasi-hydro like collisions, and then there's some new structure here, this blue one. So the red one is happening like in the previous case when the momentum scale is roughly the longitudinal relaxation scale. Whereas the blue one is occurring only at 1 over tau r. And yeah, just because now we're in different dimensions, you can decompose the correlators in terms of parity. So even in odd channels, so you have one fewer stress correlators. So I'll just focus on this density-density correlator in the even channel. So there's an additional pole, which is, I've drawn this in a funny way, but this is the branch, just moving the branch cut out of the way. You can kind of, so long as the branch points are in the same place, you have some freedom to move this. And this is what the poles look like. It's you have this usual diffusion pole, which goes like the relaxation time divided by the spatial dimension, which is 2 in this case. And additionally, you have this gapped mode, which is kind of deeper in the complex plane, with twice the well, 2 times 1 over tau r, and there's some there's some subleading terms in the small k expansion. So just to show this a bit more clearly, this is the story. Take your pick. These are the same representation of the poles. So for instance, I mean, or from small k, the poles move towards each other, and then once k is equal to 1 over tau r, they collide and they move along the essentially where the branch cut is. And actually, from this side, you can see a bit better that the real part is approaching the branch cut essentially. So when the momentum becomes infinitely large, these points will eventually, these poles will eventually catch up with the branch point. And yep. Of the, yeah, right. Uh-huh. Right. Yeah. Yeah. Hmm. That's a good way to look at it. Okay. Right. Uh, yeah. Oh, it's in the corner there. But this is, the important thing is now we have this uh, density correlator. And now instead of there being a logarithmic branch cut, it's the square root here essentially, which has the same branch points as before. Okay. And yeah, just to kind of show that, yeah, in Cataneo theory as well, but also in holography, that there's this work by Wicha-Krempa and Sachdev. This is just an example. I think this is shown in other works as well. Here they plot for different momenta, the emergence of this quasi-normal of this Christmas tree and the quasi-normal modes. The x's are poles and the circles are zeros. And so as the kind of the Christmas tree, it's this kind of unzipping basically that happens, that the poles and the zeros move apart from each other. It's kind of hard to see, but basically at some, this happens for both the zeros and for the poles. They approach each other and then they're initially all on the imaginary axis with zero real part. And then for some value of q, of momentum, they collide and acquire a real part. And they draw this picture here to kind of show the cartoon version, but this is in this particular channel, this is the same behavior. So although this is a strong coupling result, okay, we have only one pole, but they have an infinite number. This is just to show that the similar analytic structure is present, and maybe just a hint simpler to study. Yeah. The lesson from this. So I'm just saying that that this JJ correlator, so the one I was showing in the previous slide where you had, oh man, sorry. So where you have this type of collision, this type of collision we see, because we were a bit surprised when you look at the 3+1 case, you don't see this kind of collision in the density correlator, but in the 2+1 case you do. And so then, you shop around theories and you see that in yeah, two dimensions is very special. Yeah. 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 Okay. Yeah. No, it's good. Yep. Of this. Yeah. Uh-huh. You'll yeah, you'll see it's all the way down. Yeah. 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 Mm-hmm. Okay. But this was kind of an aside. Um, okay. And the rest of the structure again is relatively simple, similar. Maybe the speed of sound, like all the coefficients change because we're in different dimensions. But I kind of wanted to point out this kind of funky thing that happens at finite density and temperature, and with finite longitudinal uh, momentum relaxation rate. There's a channel with two collisions. So the red one happens at square root the spatial dimension, the relaxation rate divided by the square root of the spatial dimension, and the blue one occurs at 1 over the relaxation time. And I can try to show this. This is a little tricky to show because everything is kind of overlapping, but you have this initial collision, this one that occurs for the momentum relaxation rate. This is I show in black. So this is as a function of momentum. They're coming towards each other. There's also another pole which is above here, which is hard to see. It's given in blue with this circle here. So there's this collision. There's another pole down here which is moving, and this kind of empty circle is just to continue from this plot to that plot. So this shows the first collision, and then at later times these poles are moving away from each other, and then you see this finally this collision at 1 over tau r. And this is the quasi-hydro structure for the left plot, and this is the one for the right. And again, this is the full correlator. It's all there, all this behavior. It's a bit complicated to write down, but it's you know, it fits on a slide. Okay. So, yeah, okay. And then you can also look at it from this perspective. I mean, just looking at the real and imaginary parts. But yeah, this is the essential thing that shows the two collisions. Okay, so as an application, we can compute the thermoelectric coefficients. So there's these many different names for these things, but essentially one effect is known as the Seebeck effect, where inducing a temperature gradient, where a temperature gradient induces a voltage difference. This is due to Seebeck in 1821. There's the Peltier effect, which is the opposite, where a change in voltage generates for you temperature gradients. This is, yeah, I was in this museum of Galileo Galilei, which was excellent. I really recommend this this weekend. And here's from rooms 15 and 16, there's a section on electromagnetism. This is a thermopile. It's basically like a collection of thermocouples. And thermocouples are devices. They have two pieces of metal. I think this is bismuth is one of them, and the other one is antimony. I don't know. These are not very common metals in my everyday life, but you separate them. I mean, here there's the thermopile. It's like literally a pile of thermocouples. This is the name, from what I understand, and you can induce temperature gradients because the two metals have different conductivities. And then, yeah, you can generate an electric current. You can also reverse the process. Don't ask me how this works, why it's in this casing is, I think, for thermal shielding and stuff like this. But anyway, there's delightful, lots of things to see there. And yes, the correlators that I was talking about before, you can use them to determine these thermoelectric coefficients. So, oh, this slide is messed up a little bit, but no matter. Okay. This electric and thermal transport coefficients are given in terms of this matrix. You have some electric field here. There's a temperature gradient, and there's a matrix of these thermal coefficients. This is the conductivity. This is, I think they're called thermal power. And then kappa is the heat conductivity. And kind of, it's just helpful to write in terms of the current and the heat current as well, which is this particular combination. And then these quantities can be computed, these entries into the transport matrix can be computed directly using the Kubo formula. So in terms of JJ, and this is like the JT component, this is TJ, and this is TT correlators. So, oh man, my slides are really... Okay, so what we find, for instance, directly computing this connectivity in our model, there's this piece which is coming from the microscopic detail, and then there's this Drude peak here, which is given in terms of the number density, the energy density, and the pressure. You see that I've just written this just to save us some time in arbitrary dimension. So it just changes the power of T naught over pi. And what's kind of what's nice is that all these other coefficients are related by the word identity. So once you know the conductivity, you can determine immediately the thermal power. This alpha is equal to alpha tilde because of the Onsager relations. It should be that if I induce an electric field and that generates for me a temperature gradient, it should be if I reverse the process, I should have the same thing. I mean, it's reasonable to expect reversibility in that case. But so that was a nice check of our work in that sense. And yes, this satisfies the Onsager relations. Yeah, there's the matrix there. Yeah, and with momentum braking, the story is essentially the same. Yeah, what I wrote on the board before basically enters, this Drude peak gets softened, so there's no longer this divergence at omega goes to 0. But again, the same kind of conclusion holds in this case. How am I doing with time, by the way? Yeah, okay. 10 minutes, perfect, okay. Yeah. Do you mean just by the structure of the equations? I, so, yeah, I don't, philosophically, yeah, I don't know. I guess, yes, you would expect this, right? I don't know. You would want your, right. Yeah, yeah. So with magnetic fields, then you have to be careful because then you have an extra sign that gets introduced and stuff like this. So you have to be, right. Mm-hmm. On Sagar, yeah. Right. Detailed balance, yeah. Yeah. Okay. Good. So much about RTA kinetic theory. Let's try to go a little bit further. This is also, well, okay, it's all hidden behind these things, but I don't know a good place to put the condizione. Okay, this is a work as well with Sasha that came out recently that I'll talk about now. But kind of the motivation is for a while, kinetic theory has been really important. I mean, here I specify QGP physics, but I mean, it's also in the case of plasma physics and other recoupling settings, predictive power has been incredible, and we're able to describe a lot of non-equilibrium and equilibrium properties of matter and its transport. But kind of maybe from a theoretical perspective, it might not be super satisfying that we've fully truncated the BBGKY hierarchy down to the first level. And but I mean, okay, you have to do something in life. You have to actually do some computations, and of course, nonetheless, you see that you get impressive results all the same, such as like during Jean-Paul's talk yesterday. But the idea would be kind of the intellectual curiosity is what if we start keeping these higher particle distribution functions, so F2, F3, and so on, and kind of, yeah, I added this recently. Can we say something about about long-range correlations? Just as a I should warn you that I'm not an expert on this, but I saw this slide in Quark Matter during the summary of the last day from Bieltsikova, and kind of the slide was saying that there's some data here which for low multiplicity events where hydrodynamics and Pythia-based models are struggling to explain the data. So maybe you need to include something about long-range correlations. This is fresh for me, so I don't really have more to say about this, just that comment caught my attention. This is V2. Oh, V2, yeah. It says V2 delta 2PC, but yeah. Yeah. Mhm. Mhm. Like in the BBGKY. I'll talk about this in a second. Yeah. And channel. Yeah. This is the. Go ahead, Rajiv. It's yeah, V2. Yeah, it's V2. Yeah. Mhm. Okay, yeah. So, like I said, this is from a talk I saw in Cork Matter, which I think is just worthwhile to highlight. This is also fresh, so from April results that you can take a look at in this archive article. Okay, so good. Let me just give you a quick recap of what the BBGKY hierarchy is in the remaining time I have. So the idea is you are a master clockmaker. You have complete knowledge of all particles of n particles at a certain time t. You know all of their momenta. You know all of their positions. I mean, it's really classical. And you know then that via Louisville's theorem that the evolution is conserved in phase space. So that's this equation here. I've written this in terms of Poisson brackets. That's not super important. The n particle Hamiltonian is there's a free part. There's some external potential in principle, and then there's inner particle potentials. And I mean, this is just an example. So this is exact. It's not practical. So we can do better. You can integrate out from the nth level. You can integrate out one of the labels. So I've integrated out the nth label, both space position and momenta, and I get the n-1th distribution function. This is this reduced distribution function. And all that does is that just recasts your Louisville equation into a tower of equations. So you have the left-hand side, which is given by the nth particle distribution function, and the right-hand side knows about higher n particle distribution functions. Written in another way, I like these Poisson brackets. This is the left-hand side is kind of the free streaming term, the streaming term, and the right-hand side is the collision term, which knows about the higher particle distribution functions. But this is just a way to rewrite the BBGKY hierarchy. It's still exact, it's still unmanageable, and there should be time to truncate. So there's the typical truncation that people use is you truncate at the first level. This is what's known as the Stoßzahl-Ansatz, or molecular chaos for the people who don't speak German, I guess. I don't know. It's the idea that from Boltzmann that you take your two-particle distribution function and you just write it in terms of a product of one-particle distribution functions. And the assumption, which also hides in it this arrow of time, is that before you have a collision, the particles don't know about each other at all. And so this is a great assumption if you're in a dilute system. This is not so good if you have multiple collision events, so particles can actually be correlated post-collision. And the typical form, like I started the talk, was, okay, you can take all possible scatterings, or you can do something simpler, like, for example, take the RTA as an approximation for this kernel. And so the kind of question I want to ask is, okay, I really like the RTA because it gives you access analytically to some correlators that you can actually compute. So, and the idea is that the RTA, there's one dominant relaxation scale on which the one particle distribution function relaxes to. But if I now have many levels of the BBGKY hierarchy, there could be other time scales. So the scale on which the two particle distribution function relaxes, which I denote with tau c, and in principle, there could be a whole hierarchy of these relaxation times as the system approaches equilibrium. This is an assumption. Okay, so just this is the last slide, if I'm okay with time. But the standard form of the BBGKY hierarchy is you have, again, there's some differential operator acting on the one particle distribution function, which gives in terms of the collision kernel of the two particle and so on and so forth. This is linked all the way to n. And the kind of trick that people often do is you just decompose this into what I call uncorrelated and a correlated piece. So this is the two particle distribution function. And what's kind of handy is that the collision kernel is actually a linear, it acts linearly on F2. And so then I can write the collision kernel into divided into two pieces. One, which I approximate using the RTA, which is all of the results I'm getting for free from what we discussed in the first part of the talk. And additionally, I have a connection to the second level, which is given by this G12. Now I use the second level, instead of writing it as a function of F2, I use also the first level equations. I can write it as an evolution equation of just this correlated piece, this G12. And now the kind of where this approximation starts coming in, all of the, I allow for this uncorrelated, for the correlated piece to relax on a time scale tau c, which is in principle different than tau r. And this is then coupled to the next level. Yeah. G12 equilibrium can be zero, yes, yeah. I mean, it depends on the system. So right now I'm just agnostic. I'm just saying what the setup is. Yeah. Right, and okay, so kind of the nice thing about all this is you then have some access to these computed correlators. There's this tower of branch cuts. So we've only computed to the second level, but this is just the sound channel. Here's the sound modes. This is in 3+1 dimensions with some small attenuation. You have the branch cut from standard RTA. And now, okay, I took tau c to be at a depth of, okay, twice tau r, essentially. So that, sorry, 1/2 of tau r. So then you essentially get this other branch cut. And this is like mirroring the structure that you have at, for instance, non-interacting Yang-Mills theory. Is sigma had it, oh. Yes, so good question. I don't have this on my slides. Hold on, I can just point to you. There's a, where was this? Okay, sorry. There's a potential here, and there's a parameter. This is the sigma hat. We basically take something which is linear, and it makes really the computation very simple in that sense. But yes, it's a parameter of your interparticle potential. Right. Yeah. It enters in the potential here on the right hand side. Yeah, that's right. Okay. Right. That's right. Yeah. 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 That's right. And we can also do this for the diffusion and everything. I just realized I'm out of time, so I wanted to tell the first part of the story, and yeah, go ahead. Yeah. Oh yeah, you mean the functional dependence? Yeah. It's like F2. So G12 depends on time, the label for momenta, and X2, P2. And so this, and so this is compute. So the kind of the thing you do is you solve. So what we do for this plot, we truncate here. So we put this to 0. You solve this. You plug it in here. You integrate out the second particle label. And then so this is like, so like the structure up here is literally, if I put sigma to 0, like this branch cut disappears. This is the, yeah. Yeah, you would get, so sigma we're treating as a small parameter as well. So this is kind of an expansion in sigma for now. Yeah. Yeah. Mhm. Density dependent. Hmm. Yeah, I mean, we just have this parameter tau c essentially, but I'm interested to hear more about this. I don't know. Yeah. Yes. Yeah. Yeah. That's right. Yeah. Yep. Hmm. 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 Very hostile way to ask this question, pitting the participants against each other. I like what I would say is why like I'm aware that about the sign question and kind of why I think we were um, okay with the sign being decreasing is because the idea would be we're going okay in some sense this is people have done finite coupling corrections from the gravity side and you get the shear viscosity increases the ratio, right? And here we're kind of doing the opposite direction. We're starting from kinetic theory and we're making it more less dilute, right? So this is kind of stronger interacting in some sense. I use this really in quotation marks. So, I mean, are they coming towards each other in terms of interpretation? I don't know. Hmm. Right. Yeah. This is literally the last slide. Yeah, I just, yeah. Hey, just the summary, I just flashed this. Yeah, just to kind of, but what I really wanted to convince you guys is that in the kinetic RTA, we can compute the complete analytic set of correlators for the thermoelectric effect. So this at finite temperature chemical potential, and even including momentum relaxation. This gives you direct access to dispersion relations and transport coefficients. It's a lovely set of computations to do. And there's like a few directions that I just want to highlight. I mean, this previous section of going beyond the RTA and trying to use the elegant simplicity of the RTA to maybe say something about the BBGKY hierarchy. Some things that we haven't included is a momentum-dependent relaxation time. That like such as Kurkel and Wiedemann did in 2017. But also, what about in the presence of magnetic fields, if massive particles, you can have many species, long time tails, stochastical fluctuations, and things like this. So with that, I just wanted to thank you for the attention, and yeah, I'm here for any questions. Copy. Mhm. Thank you.